Hi everyone, my name is Aditya K. Kamath and I'll be presenting iGUARD in GPU Advanced Race Detection. Let me start off with a brief summary of what we'll be covering. We'll start by talking about advanced GPU synchronization used by emerging GPU use cases, which can cause new bugs when improperly used. We then propose iGUARD, a race detector that uses binary instrumentation. iGUARD performs race detection within the GPU, providing low overhead. It detected 15 previously unreported races in popular open source applications and libraries. Traditionally, computation on GPUs have used bulk synchronous parallelism, such as in matrix multiplication. Nowadays, applications running on the GPU are more irregular. Applications like encryption and graph processing have more complex needs. They demand semantically richer synchronization to support them. In addition, every GPU generation is also getting larger, making global synchronization more expensive. Here we can see how the trend of NVIDIA GPU sizes in number of concurrent executing threads is constantly increasing. A similar trend exists for AMD GPUs as well. So not only do we need more complex synchronization, but this synchronization should also scale to the growing sizes of GPUs. GPU vendors have responded by introducing advanced synchronization, which we shall now see. The first advancement in synchronization is scoped operations. A scope qualifier, when used with a synchronization operation, specifies a subset of threads for which the synchronization is guaranteed. A warp is the smallest unit of scheduling, consisting of 32 threads executing in SymT fashion. Many warps make up a thread block, which is a group of threads guaranteed to execute within the same multiprocessor, while many groups of thread blocks make up a grid, which are the threads executing a common GPU kernel. Different scopes can be used to synchronize within these groups of threads. By using a narrower scope, the overhead of the operation is reduced. For example, a device scope fence guarantees visibility for the entire grid, while a block scope fence only guarantees visibility within the thread block, but is 20 times faster than the default device scope on a modern GPU. While scopes can provide performance benefits, they can also be a new source of races. If two threads attempting to communicate through a common memory location use an insufficient scope for synchronization, the synchronization is not guaranteed, causing a race. The next advancement in synchronization that we look at is independent thread scheduling. Conventionally, threads within a warp executed in lockstep, with implicit synchronization after every instruction. With ITS, threads now execute independently, removing this implicit synchronization. To understand why ITS is useful, we take an example CUDA code snippet seen on the left, which all the GPU threads execute. Here, two warps are competing to acquire the same set of locks. Assume a subset of both warps manage to acquire their respective locks. The threads which fail to acquire their locks will be stuck waiting for the threads in the other warp to release their locks. Due to lockstep execution, the threads which successfully acquired their locks are forced to wait until the other threads in their warp also acquire their locks. This leads to a deadlock. Instead, with ITS, the threads that successfully acquire their locks can proceed with their execution, removing the deadlock. However, the introduction of ITS can also create races in previously race-free code. This is because the assumption of implicit warp-level synchronization is now broken. Threads within a warp that relied on this synchronization now race with one another. To solve this, new warp-level barriers have been introduced, which should be inserted at appropriate locations to explicitly synchronize these threads and avoid the race. The last form of advanced synchronization that we look at is cooperative groups. Cooperative groups is an NVIDIA library that allows users to maintain and synchronize groups of threads as explicit data structures. It also provides users a way to define their own custom thread groups, providing a flexible means of synchronization. Internally, CG makes use of existing synchronization primitives to implement these flexible synchronizations, abstracting away the details from users. When a user misuses the library, it can cause a race. For example, In this CUDA code snippet, the sum of an array is found in parallel as a reduction operation. First, the array is divided equally among the executing thread blocks, with each thread block finding the sum for its assigned subarray. This is done in the function reduceBlock seen on line 5. Following this, a single thread finds the sum of the output sums that each thread block generated, seen on line 9. To ensure that this is done only after the thread block sums are calculated, synchronization is used on line 6. However, as synchronization is only within individual thread blocks and not the entire grid, it causes a race. While GPU race detection is not a new topic, we notice that prior work have many limitations. For example, they do not support all the features that modern GPUs have, such as races caused by ITS. While low overhead detectors exist, such as our prior work scored, these require significant new hardware to be introduced. As such, our goals with iGUARD is to provide a comprehensive coverage with lower overheads that does not need recompilation. This detector should be implemented purely in software with no new hardware. We shall now take a look at iGUARD's design philosophy. First, the application, colored in blue, begins execution on the CPU, where all memory and synchronization operations in the GPU kernel are instrumented for race detection using NV-bit, colored in red. Binary instrumentation allows us to avoid recompiling the source code. This instrumentation captures the details of scopes used and the threads performing the operations. A key part of our high performance is that the entire process of detection happens within the GPU. Because of the large number of GPU threads, pairwise comparison is infeasible. Instead, for each unit of application data, we keep some metadata that tracks the previous writer and accessor of that data. This metadata has details such as thread ID and locks held during the access. When performing race detection, this metadata is fetched and used along with the details of the current accessor. The detection logic uses happens before and lockset detection extended for advanced synchronization. The details of the current access is checked for a race against many conditions. First, we perform preliminary tests to see whether there is no possibility of a race. For example, we check whether this is the first access to the data item, or whether the data has been accessed by only a single thread with no interleaving access by other threads. If any of these tests pass, we stop detection as the access is safe. If all the preliminary tests fail, we perform more detailed detection where we check for missing synchronization. If any of these tests pass, the access is declared a race. Otherwise, the access is safe. Full details of the different conditions we used can be found in the paper. The details of the races caught are kept in a buffer in the GPU, which is later sent to the CPU. These details are then reported to the user. There are many unique challenges that we encountered. The first is that metadata can end up hogging the GPU memory, limiting the size of memory that the application can use. Also, GPUs thrive on parallelism, which the performance of our detector depends on. However, many threads may concurrently access common data, which requires serial accesses to metadata for correctness. In addition, with ITS, individual threads can acquire a lock, or the entire warp can acquire a single lock. We must infer the protocol for locking used by the application kernel. The amount of memory needed by an application combined with the size of metadata may exceed the limited memory capacity of a GPU. To resolve this, we make use of a feature present in NVIDIA GPUs called Unified Virtual Memory. This feature allows us to reserve an amount of memory that exceeds the GPU memory capacity. Excess data is kept in the CPU memory. Whenever the GPU requires data kept in the CPU memory, it is migrated between the CPU and the GPU. Note that this migration only happens when the GPU memory is insufficient. If we notice that the application data and metadata can both comfortably reside in the GPU memory, we keep it there. Another problem that arises is when multiple threads access a common data location. For correctness of race detection, the accesses to metadata and race detection logic must be serialized. We do this by using fine-grained locking for each metadata unit. The resulting serialization and contention is adverse to the performance of a GPU, which relies on parallelism. To address this, we use two techniques. Concurrent read and atomic operations from within a warp cannot race with one another, as a warp is smaller than the smallest possible scope for an atomic operation, which is a thread block. If we notice multiple threads from within a warp concurrently performing these operations on a common data location, we assign a single thread from the warp to perform race detection and metadata access on behalf of the entire warp, coalescing these operations. This reduces the number of serial detections by up to a factor of 32, which is the size of a warp. Furthermore, to reduce lock contention, we use exponential backoff during locking. We notice that the greater the number of concurrent threads executing, the larger the contention. So, we dynamically scale the backoff limit based on the number of concurrent threads in the kernel. We found that these optimizations sped up race detection by up to a factor of 123x for certain applications. With ITS, locks can be acquired by individual threads, or a single thread can acquire a lock on behalf of the entire warp. To ensure correct lock set functionality, the detector needs to be aware of the protocol being used. To do this, we first track the locks at a per warp granularity, where all threads within a warp share their locks. During lock acquires, we use the GPU warp intrinsic active mask to check whether at least two threads from within the warp are attempting to simultaneously acquire their locks. When this occurs, we switch to tracking the locks at a per thread granularity. Now that we've gone over how iGUARD functions, we'll see how effective it is at catching races and the performance overheads associated with race detection. We perform all our experiments on a modern Intel server with an NVIDIA Titan RTX GPU. We use the latest major CUDA version, which is CUDA 11. We demonstrate the usefulness of iGUARD by detecting various races that were previously unreported. For example, iGUARD caught 12 new races in popular open source repositories Gunrock and Lone Star GPU. In addition, it caught 3 races in NVIDIA supported libraries. In total, iGUARD caught 57 races across 21 applications and benchmarks. Here, we see a simplified CUDA code snippet from the CG library where we detected a race. This function is executed by all the threads in the grid in order to synchronize them. We'll first see how this code is supposed to function, then I'll explain how it can create a race. First, line 4 contains sync threads, which is a thread block level barrier. It ensures that all threads are forced to wait until their entire thread block reaches that point. The if condition in line 5 ensures that lines 6 to 9 are executed by a single thread from each thread block, which we shall refer to as the leader thread. Line 6 contains a device scope fence that ensures all previous memory accesses by the leader thread are visible to all other threads in the grid. In line 7, the leader thread increments a variable arrived. This variable keeps track of the number of thread blocks that have reached the function. Line 8 forces the leader thread to wait until arrive becomes equal to the grid size, at which point we know all thread blocks have reached this point. The thread block level barrier on line 10 ensures that while this process is happening, no other threads within the thread block are allowed to proceed with their execution. This ensures that all the threads in the grid reach the function before any thread is allowed to leave. Notice that the device scope fence is only executed by the leader thread of each thread block. This fence only guarantees visibility of memory accesses for the calling thread. Consider two threads A and B in two different thread blocks, neither of which are leader threads using common memory location to communicate, here x of 0. A safe assumption should have been that separating the write and read operations by the sync grid function would provide sufficient synchronization to avoid any races. However, as A is not a leader thread, it would not execute the device scope fence. Instead, it would only execute the thread block level barriers seen on lines 4 and 10. As thread B belongs to a different thread block, this is not sufficient synchronization, so these two threads are part of a race. Instead, if the device scope fence was moved to line 3, this would guarantee that thread A executes a device scope fence, which would then synchronize with thread B. Not only did iGUARD catch a wide set of races, but it also did so at a lower performance overhead. Here, the graph compares the overhead of iGUARD against a previous work Barracuda. A detailed breakdown of the graph is given in the paper. Across all the applications, iGUARD was faster than Barracuda and on average performed 15 times better, thanks to iGUARD's in-GPU race detection. It also did not miss any races caught by Barracuda. On average, iGUARD had a 5.1x runtime overhead. To summarize, concurrency bugs threaten GPU applications. Newly evolving programming features also come with the possibility of new bugs. To combat these bugs, we propose iGUARD, a race detector with low overhead that requires no hardware changes and supports advanced synchronization.